It begins with a spark.
Hey Jackie, wait for me.
The passion for air and space.
Why don't you take it? It'll look better on you anyway.
Hey Jackie, remember her?
That passion can grow. Lighting the way forward for a lifetime. And now, with the monumental transformation of the Smithsonian's National Air and Space Museum, this place that has ignited generations of imaginations will be completely reimagined, inside and out. Also, this museum can be even more of what it's always been. A place that gives life to a remarkable past and gives rise to the people who will make history tomorrow. Join us in the mission to transform the National Air and Space Museum. Together, we'll ignite tomorrow.
Hi, good evening. I don't know about you, but that video always gives me chills. Maybe it's because I'm new here and I'm still really giddy about being here, but welcome to the National Air and Space Museum. I am delighted to say that I am the Brocon Wheel Director of Education. My name is Beth Crownover. It is my pleasure to welcome you to tonight's GE lecture, all about history and future of supersonic flight. Like I said, I'm new to the museum, so everything is really exciting to me, but I think this is going to be a really good one, especially after some of the stories shared at dinner. As you may have noticed, when you came into the museum tonight, we're in the middle of a little bit of a transformation. And our building here on the National Mall is under construction. When we have finished redesigning and updating all 23 of our galleries, the new National Air and Space Museum will tell transformative stories of aviation and space in new ways to new audiences, allowing us to reach further than ever before. This is a mission near and dear to my heart as a museum educator. I've seen how this museum can inspire people to do incredible things, and this project will allow us to continue to provide inspiration to our visitors and encourage them to achieve the next great milestones in aviation and space, like we just saw in the video. We're about a year into this multi-year renovation, but don't worry, we'll be staying open the entire time. So we invite you to continue visiting and attending events like this one tonight. Even if you see cranes and fencing outside, we'll still be here to share the stories of aviation and space like the one our speakers will tell tonight. The GE Aviation Lecture Series is the museum's longest running sponsored program. We've hosted more than 150 of them since 1982. Thanks to the support of GE Aviation, we have been able to provide access to these programs free of charge, both for those of you attending here in person and to everyone watching through this live simulcast. Representing GE Aviation in the audience tonight is Darby Becker, Government Relations at GE Aviation. Thank you for joining us tonight, and thank you for the continued support of the museum. Supersonic flight is a topic that always delights and amazes our visitors. From marveling at how Chuck Yeager had the right stuff as he piloted Bell X-1, to longing for the speed of the Concorde when we board flights to the other side of the world, supersonic flight holds a certain mystique. So we're excited to share with you tonight the stories of supersonic aircraft past and the exciting future for this field of aircraft design, including NASA's work on quieting the mighty sonic boom to a thump and Boom's work on the next supersonic airliner. But like all great stories, we have to start at the beginning. To kick us off, I'd like to introduce National Air and Space Museum curator Bob Vanderlinden, who, by the way, got to fly on the museum's Air France Concorde on its final flight to DC. Yes, we are all jealous. Please, Bob, I'd like to welcome you to the stage.
Thank you very much. I'm delighted to be here. Unlike Beth, I have been here a long time. But it's still exciting for me every day. I got the best job in the world. I get to come play with my airplanes every day. Thank you all for coming, especially on a wet night. This is a very impressive crowd for a Monday, for any time. This is terrific. That doesn't poke me in the face. 50 years ago, the graceful Concorde supersonic transport first took to the sky. A product of the best British and French aviation technology, it symbolized the arrival of the future. In 1976, the Concorde carried its first paying passengers across the North Atlantic, cutting travel time in half. It became the preferred mode of travel for the rich and famous and served as a prominent demonstrator of Anglo-French cooperation and aerospace prowess. Yet 27 years later, the last Concorde was retired. Why? High costs, high fares, loud noise, and the absence of an expected market caused its undoing. Only 20 Concordes were built for only 2 airlines. Not surprisingly, they were British Airways and Air France, the national airlines. No other airline wanted it. Well, they did want it, they loved it, but they ran the numbers on it and it was just too expensive for them to operate. So in late 2003, the last Concorde completed its last commercial flight. That future is now the past. Or is it? Today, there is a renewed interest in supersonic travel. There are new technological innovations that are leading to renewed hopes for its return. Our guests this evening are participants in this revived dream. Each will speak briefly about their role, followed by a moderated discussion. We will end with questions from the audience. I hope you have some good ones. To set the tone for this evening, we're pleased to have with us Lawrence Azerrad. I'm sure I'm mangled it. Yeah. With a name like Vanderlinden, it gets mangled too. The founder and creator and creative director of LAD Design Incorporated, who will provide us a reflection on the glamorous career of the Concorde. He is the author of a beautiful new book, Supersonic, The Design and Lifestyle of Concorde. Do a plug here for you. Well, you'll see the inside. This is a gorgeous book. He will also host a book signing at the end of the program this evening. Ladies and gentlemen, Lawrence Azerrad.
Space Museum, the Smithsonian, to GE, to our colleagues tonight, Boom, Supersonic, and to NASA, of course. And thank you to all of you for being here tonight in the rain. I'm from Los Angeles. It's a really big deal when it rains and everything stops. But the story of Concorde is much more than a story about an aircraft alone. It's really about the power of design to unify, inspire, and uplift us. To see through design a reflection of our best selves and what we can do when ingenuity, creativity, and determination come together. Throughout the dawn of history, it's really the risk takers, the disruptors, the innovators, as it connects to transportation, that moves the human story forward, all the way to this footprint here on the surface of the moon. Which is why I have to say that sometimes, to see our best future, you have to look backwards. 2:52:59, that's hours, minutes, seconds of the fastest transatlantic Concorde crossing. That's just 7 minutes short of 3 hours. To put that in a little scale and perspective, that Spirit of St. Louis that's mounted from the ceiling right outside from the doors at where we're sitting tonight made that same journey in 33.5 hours. So this was considerably faster. Concorde flew 1,350 miles an hour. That's twice the speed of sound, but also faster than the rotation of the Earth itself, allowing passengers to famously get to their destination before they actually left in real time. Because you could half any flight distance and you could get to your destination and cut any flight time in half, you made the world a smaller place. But you also brought together people through a unified goal. And that's what's so exciting about the story of Concorde. You look back at these ideas of the future, and some of them can seem a little tentative. Cars inspired by the idea of flight, buildings inspired by the idea of flight. Here you have Aero Saarinen TWA terminal, and then closer to home here in Washington, the Dulles terminal. Cars and buildings that looked like they could fly, but of course they couldn't fly. It was Concorde that could fly and flew beautifully, all a reality that served as an emblem of possibility. The era of Concorde brought a palpable hopefulness for a better future, a spirit of curiosity and optimism, an idea of a better world to come. It's all about an idea of tomorrow delivered in the here and now, where the sky is no longer the limit, all manifested through ingenuity and creativity. Here's another view brought to us by ingenuity and daring in transportation, brought to us when we answered the call that President Kennedy said, we choose to go to the moon because that goal will serve to measure and organize the best of our energies and skills, because that challenge is one that we're willing to accept, one we're unwilling to postpone, and one which we intend to win. So, as Bob indicated, many airlines wanted to fly Concorde. This is an example of all the stewardesses that had plans to fly Concorde. United Airlines, TWA Airlines, Pan Am Airlines. Here's a picture of the plans on the site map of my home airport. You can see the Delta Wing Concordes lined up at the gate, serving as evidence that people fully expected that this would be the next logical step in transportation. You had propeller aircraft, then jet aircraft, supersonic aircraft was the next logical step, of course. What happened is you had the battle over volume and speed, and then there were also the issues that Bob mentioned, and also geopolitical challenges. The bottom one is the American supersonic that Lockheed and Boeing were making, and it ended up getting too expensive to get off the ground. This is the Soviet version that did actually fly the Tupolev 144, which they also nicknamed the Concorde ski. And here you could see them all three together in terms of scale. This is a picture that I took from my flight. Concorde flew at 60,000 feet, which is twice the altitude of regular airplanes. So from that altitude, the sky is black and you could see the curvature of the Earth, and you are actually in the troposphere. So it is as close as you will get to being in outer space until the next generation of supersonics comes along. So my book is meant to be a reflection of that exuberance of optimism, of hope, of inspiration that came so much from the era. The idea that children would be playing with toys that reflected these ideas of innovation and ingenuity. In the foreword for our book, Sir Terence Conran, who designed for Concorde, said that Concorde had a magic ingredient of the truly special, and it inspired the imagination of millions of people all over the world. It was, of course, the shape, a true case of form following function, as beautiful as a sculpture, graceful as a swan, but as practical as a paper airplane. It was the shape that allowed Concorde to be the only aircraft that could maintain a supersonic speed without the use of afterburners, and that's a record that still holds true today and includes military aircraft. Of course, it was the Rolls-Royce Olympus engines that was able to get Concorde up to that speed by delivering 38,000 pounds of thrust, or 18.7 pounds of thrust. Once the airlines, the two airlines that were stuck with Concorde, Air France and British Airways, were left with this very small fleet, they turned to an ecosystem of design to make this spectacular passenger experience as memorable as possible. So everything that you came into contact with had the forethought and elegance and exuberance of Concorde's mission. This is the interior of Raymond Loewy's Air France Concorde, looking very much like something out of Stanley Kubrick's 2001. Andy Warhol used to love to steal the Raymond Loewy silverware. But passengers like Warhol kind of reflected a new class of superstars and the world's kind of elite that loved Concorde for its speed, such as the Queen of England, or the Pope, or heads of rock and heads of state. That's Prime Minister Jacques Chirac in the color picture. They also extended the passenger experience to the lounges, surrounding passengers with these great icons of 20th century design, all before you stepped on one of the great icons of 20th century design. Even in the 1970s version of the lobby, kind of extending that idea of the future through design and the environment. Uniforms designed by Sir Edwin Ames, the Queen's fashion designer, menus designed by Christian Lacroix. Everything you touched had the elegance and exuberance, optimism, and vision of Concorde. Even the interiors, luxurious in its tightness, almost like a sports car. There was an economy of space, so it became kind of a situation where nothing more or nothing less than was absolutely necessary, and an elegance in the restraint of design. Of course, it was sad on the last flight of Concorde, because until my colleagues who are going to speak about the next generation of supersonic, you're stuck in this situation where we went backwards. At 2003, we no longer had the supersonic flight, and it's somewhat of a challenging moment, because there's this idea that we can do better. This idea that in our history of design progress, we rarely go backwards. And my studio does a lot of work with Jet Propulsion Laboratory, and as you walk into JPL out in California, there's this sign, Dare Mighty Things. And if you're a parent or a teacher or a designer or an engineer, it's a maxim that I think we could use more of today and as we move forward into the future. And that's really the story of Concorde, is that it's about the idea of people inspiring in others this spirit to dare mighty things, to do things differently, to do things better, to elevate the human experience, and to make the world that we live in better through innovation, creativity, determination, and design. Concorde was not perfect, but if we could design a vehicle that could do this, or a vehicle that could take us to the outer reaches of the solar system, or if we could design this, perhaps we could design the vehicles that will take us into the next chapter of our future. It's as the French designer for the Air France interiors of the Concorde, the great architect and interior designer André Putnam said, to not dare is to have already lost. We should seek out ambitious, even unrealistic projects, because things only happen when we dream. Or as Apollo 8 astronaut Bill Anders said, we came all this way to explore the moon, and the most important thing we discovered was the Earth. I ask, can we return to these ideas of progress? We have the capacity, an obligation to design, engineer, and realize the future that we should have today and tomorrow. It's time to show the world this kind of future again. Thank you very much.
Thank you. Oh, yes, gentlemen.
I'll let you pass.
You're too kind. You'll be getting up in a moment anyway.
Right.
I can tell you from personal experience, it's a shame they couldn't make the Concorde work. Because my word, be able to get home from Paris in less than 4 hours and having eaten one of the finest meals you'll ever eat, it's a shame they couldn't make it work, because that is flying, believe you me. Our next speaker is leading the effort to return a new generation of supersonic transports to service. Here to discuss this plan is Joe Wilding, the co-founder and chief technical officer of Boom, a private company working on supersonic flight, focused on building history's fastest commercial airliner, Overture.
Thank you. So I want to first shout out a very large thank you to Lawrence. There you go. You did a fabulous job of telling our story. So this is what we are doing at Boom on a daily basis. At least we're trying. We're trying to bring back all the vision and the excitement and inspiration that you just spoke of. And hopefully, if we can be successful, we can do it in a way that's much more mainstream and in a way where everyone in this room can experience that, not just a couple of people like the Pope and the Queen and so forth. So I'm going to start you with a quick video that really gives you a visual and a little bit of a musical intro into what we're doing at Boom and how exciting it is. So I'm going to show that, and then I'll come back and talk a little bit more in depth about the story and what we're doing.
Walking away from you. That's what I'm gonna do. With a new attitude, why would I sing the blues for you? I say, hey, you can't stop me, 'cause my pain, is gasoline. I can't wait. If you break my heart, it's 1, 2, 3. Boom, boom, boom. My feet go boom, 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 boom. My heart beats boom, 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 boom. Heart speed goes zoom, 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 zoom. My feet go boom, boom, boom. Walking away from you.
Isn't that fun? So all of those pictures you saw are from our hangar in Denver. We're actually building this first third-scale demonstrator right now. Before we get into that, let me tell you a little bit more about the backdrop of Boom and kind of how we got to where we are and why we're inspired to do what we're doing. So I flew here to DC this morning from Denver, and I'm a huge, huge, huge aviation fan. I love flying. Nothing makes me happier than getting on an airplane. I will tell you, though, as most of you know, anybody who's gotten on an airplane in recent years, the experience is a little bit different than what Lawrence was showing in his imagery from the beginnings of the jet age. Somehow we kind of lost the glamour of it. And the experience today, there's impediments that get in the way of great air travel and ultimately experiencing the planet. That's really our vision at Boom, is to let more people experience the planet. And the three hassles that we tend to experience are cost, time, and just the hassle of travel. So dealing with security, grumpy passengers, delayed flights, and so forth. So at Boom, our vision is to make the world more accessible by breaking down those barriers, the time, the cost, and the hassles. The first one we're really focusing on is the time aspect of it with our supersonic airliner Overture, which you can see behind me here. So our entire team is really a bunch of aviation buffs. We are tremendously inspired by Concorde and what Concorde was able to do 50 years ago, starting 50 years ago. So Concorde is an amazing technological advance. The fact that this airplane actually was built, was successful, and was certified back in the 60s still just blows my mind. That said, it was not an economical success for some of the reasons that our two speakers tonight here have already pointed to. It just really didn't make economic sense on the fuel burn and the cost to operate based on the fleet size. And so we believe at Boom that we can build an airliner that solves those problems. You fast forward 50 years, there's 50 years of technological advancement. So think back to the way engines and cars and power plants and everything looked 50 years ago and what the world looks like today. Well, all the same advances have happened in aviation. So at Boom, what we are doing is we are capitalizing all those advances that exist today. We're really not inventing any new technology at Boom. We're taking today's supersonic technology or subsonic technologies that are certified and delivered in airplanes and putting them together in a supersonic airplane that basically goes and solves the same mission. So our Overture aircraft, it's a little bit smaller than Concorde, 75 seats versus 100 seats, but it's a little bit faster. So we're going to go Mach 2.2 instead of Mach 2 that Concorde went, and we have a little bit more range. And we believe if we can bring that to market with today's technologies, we can come up with an airplane that is efficient enough that we can offer ticket prices, or the airlines I should say, but an airplane that can offer ticket prices that's competitive with today's business class tickets. So again, you don't have to be the Queen or the Pope in order to afford those tickets. Anyone today flying on a business class seat, which is about 65 million passengers a year, should be able to afford a ticket on our airplane. So that's really the market that we're going after. The status of where we are right now, so we're building what we're calling our XB-1 aircraft that you saw imagery of in the video and pictures of the assembly. That is a 1/3 scale technology demonstrator, 2 seats. It'll go Mach 2.2, so it has the full speed capability of the eventual Overture aircraft. And what we're doing with that aircraft is proving that this technology works and proving that we can get to the efficiency levels necessary to make this project viable. So that is in work right now. Later this month, you'll see a virtual unveiling of that where you can track the progress as we finalize the build and the assembly of the airplane, and then as we move into the test phase next year. Overtures in the early design phases. We're in a conceptual design phase right now. We're working with engine companies to develop an engine. We'll hear more about engines tonight. And that airplane will be developed over the next few years and then get into the testing phase in the mid-2020s. So as a company, we're about 140 people right now. We've raised about $150 million in funding. Our demonstrator that you saw is fully funded through Supersonic Flight. So everything you see there that we're working on will get to that stage in the coming year. I think that's the summary of where we're at. I'm super excited to continue this conversation with the rest of the group. Thank you.
Thank you very much. Okay. NASA and its predecessor, the NACA, have pioneered aviation innovation for more than 100 years, solving technical problems for the American aerospace industry. Every airliner flying today carries NASA DNA in it, although most people don't know that. Our next speaker is Peter Coen. He's the manager of NASA's low-boom flight demonstration mission to design and build a piloted large-scale supersonic X-plane with technology that reduces the loudness and the impact of sonic booms, critical if SSTs are ever to fly again. Peter?
Thank you.
Good evening, everybody. Pleasure to be here. Not quite as flashy as Joe. I don't have a video. I think our song would be something more like "No Boom, Boom, Boom," but that's okay. NASA, NACA, the National Aeronautics and Space Administration, the small a, the important A in NASA. And as Bob said, we're all about solving the problems of, studying the problems of flight with view to their practical solution. So what NASA Aeronautics tries to do is develop technologies and methods and solutions that really enable a transformation of global air transport. So certainly not just supersonics. As Bob mentioned, our DNA and NASA technology can be found on almost every airplane flying today. But supersonics, I mean, how transformative, and Joe's talk certainly said that, is how transformative can decreasing your flight time by a factor of 2 or more really be in terms of worldwide air transport, particularly with the increasing globalization of air transport and the longer distances that people want to fly. So NASA's been working this for a long time, again, as Bob mentioned, but we really represent a community that's really looking to bring supersonic aircraft to a broad spectrum of the traveling public in the future. So it's not just the Concorde, not just the Pope and the Queen, but you and me and business travelers, et cetera. So our vision really is that supersonic aircraft can fly over land without creating a disturbance, disturbing sounds, and compared to Concorde, be efficient, affordable, and environmentally responsible. So there's a lot to be done to make that happen. And national research agencies such as NASA and national and international policy agencies such as the FAA and the ICAO play an important role in bringing technology and policy to bear that can essentially open a new market. Because as we all know, right now, supersonic flight almost worldwide is prohibited because of the disturbance created by sonic boom. So in NASA's vision, overland flight is really a key thing that really would break, ultimately, the barrier to supersonic airline operations in the future. One of the reasons that Concorde was not successful is because with supersonic overland flight restrictions, the airlines could not use them the way they wanted to use them. They lost more efficiency by either having to transfer passengers to subsonic airplanes or, heaven forbid, fly the Concorde at subsonic speeds over land, although that was tried. So the airplane that you see here is not a real airplane. It's not going to be a product, but it is the result of studies that NASA did earlier in this decade to try and figure out if our technology that we had developed to reduce the sonic boom to a sonic thump actually could be integrated into a real design and be successful eventually with the right technology suite for supersonic airline operations. And it was. So we figured what was the next step? Well, we really would like to flight test that technology because there's a lot to be learned about the sound and how the atmosphere affects it and how different flight operations affect it. But the real advantage we saw to taking the next step and going from a paper airplane to a real X-plane was that we could actually use that as a way of collecting data from the average person going about their average, their daily business, and understand how quiet the airplane has to be acceptable to enable the rule change that's needed, essentially to change from prohibitions to certification standards that allow designers, companies, to build products. They know they know the goalposts that they have to reach and can build airplanes that are acceptable for supersonic overland flight. So we set out on the low boom flight demonstration mission. We had 3 goals: essentially design and build an X-plane that proves our technology that creates a soft thump while flying at supersonic speeds, fly it in the ranges over our Edwards and Armstrong flight research facility in California to prove that it's safe. But ultimately, the really thing is to use that X-plane in a series of community overflight tests where we will engage you and others across the United States to determine what level might be acceptable for supersonic overland flight. So that is the mission that we've started off on. This is the X-59 Quest aircraft. NASA recently, a year ago, signed a contract with Lockheed Martin as our partner to build the airplane. The airplane is in fabrication now. We expect it to fly in 2021. And the X-plane approach is really, it's historical. We talk about the X-1, and it's really all about if you have something that you really want to prove, selecting the minimum set of requirements that are needed and going about it in a way that enables you to get the answer you need in as expedient a fashion as you can. So that's what the X-59 is all about. Really the key requirements are, this is an airplane, it's big, it's 100 feet long, but it's only single engine, single pilot. It's not a prototype for a future supersonic airliner. but it has to have the acoustic characteristics that are representative of future supersonic airliners. So that's the main design ingredient. And then you have to be able to fly it in a manner that represents how future supersonic transports might fly. So those were our key requirements. Like I say, it's 100 feet long, single engine, Mach 1.4, cruise at an altitude of 55,000 feet. Again, we expect our first flight in 2021 and begin our community tests in 2023. We're partnered with the FAA and the ICAO, the international body that sets standards for safe and environmentally responsible operations worldwide. And the idea is to deliver to them that data, which they can then use to essentially set the standards that will really open the market for a new experience in air travel, supersonic flight, overland, and in airline operations. So thank you very much.
Thank you very much. GE has led the development of jet propulsion in the United States from the very beginning of the jet age. Their first engine, the GE-1A, powered America's first jet aircraft, the Bell XB-59 Aerocomet. That aircraft is hanging proudly in our Boeing Milestones of Flight Hall, just on the opposite side of that wall, in a place of honor. GE continues today as the world leader in jet propulsion. Our final speaker is Joel Kirk, the Executive Leader, Advanced Systems Design and Technology, GE Aviation. Joel.
Hand me that. Good evening. Yeah, go ahead. Go for it. Does anybody need to stand up and stretch a little bit? Okay. I practiced this in the hotel room. I got it in 43 minutes, so sit back. Okay, look, you know, it's an exciting time to be in aviation. There's a lot of interesting things going on, supersonic being one of them, and we're happy to be a part of that. And Joe mentioned earlier about using current technology to go execute a supersonic aircraft. He mentioned that technology has changed in the last 50 years since we tried to do it on the Concorde. And I'm going to talk a little bit about some of those changes. There's about 15 to 20 different topics I could talk about. I'm going to focus on 3, and that is emissions, durability, and noise, and relative to the engine, which, as an engine designer, I believe is the most important thing on these aircraft. But I'm going to start the conversation the way we start every conversation at GE Aviation anyway, and that is to remember that our focus is on safety being priority number 1. In our industry, we have to be correct every time. We can have 0 misses. Every time we have to be correct. Now, I've tried to use that line with my wife. I've told her that I am always correct, and I'm a professional. Surprisingly, it didn't go over as well there as it does at work. But what I'm showing here is our test platforms, the GE flying test beds where we test all of our engine development programs. And that is the culmination of a long series of testing that we do for all new technology. So as we talk about new technology and new aircraft, I just want to set the table with that there is a rigorous process for all of us to develop these new technologies and get new products into flight. So with that, let's dive into the 3 things that I talked about before. And the first one is going to be around reducing emissions. As an industry, we've made a commitment to reduce emissions between now and the year 2050 by 50%. That's a challenging thing to do because all of you want to fly more and more, so there's more flights flying every day. And in 2050, a lot of the aircraft you're flying on today will still be in service, so they won't have the benefit of new technology, right? And so this is something that we're working on as an industry to get our performance, our fuel burn improvement, so that our emissions reduce. And we do that through 3 things. One is better performing engines, lighter weight engines, right, and lower emission fuel capability. So real quick, you didn't think an engineer was going to talk here without, oh, by the way, I didn't tell you, I'm an engineer. Without showing some equations, this is the introduction to aircraft engine design. And it really comes down to the efficiency of a turbofan engine, which every commercial engine is. Comes down to 2 things. One is thermal efficiency, which means I want to burn the fuel as hot as I can compared to the inlet air coming in. And you didn't know that, but you don't realize, but you already knew that was the definition of thermal efficiency, because every single one of you over Thanksgiving, when you put a pot of water on to boil, did any of you put the knob on low, or did the burner go straight to high? The burner went straight to high because that was the most efficient way to bring it to a boil. The second piece of efficiency is propulsive, and that is that the velocity of the air coming out of my engine, I want that to be as close as possible to the velocity of the airplane. And essentially think of this as, if I can move all that air through a large area versus blowing the same amount of air through a small straw, I do it more efficiently. Now that's a trade for supersonic flight, because that large area creates a huge frontal area that creates drag. So that's one of the trades we're going to make on how to fly supersonically most efficiently. So I went through that quickly, but you now know as much as I know about aircraft engine design and what it takes to make it efficient. Our industry, on average, is improving about 1% per year, and that's been consistent for the past several decades. So 15 years from now, our products will be 15% better in performance. Doesn't sound like a lot, but compare it to some other industries, automotive and power, and it's actually really good. And it's the result of billions of dollars of investment across the industry. But to get to our targets, that's not enough, and so we have to start talking about alternate fuels. So this emissions piece is a headwind for supersonic, not to use pun intended, by the way. And so there's a two-phase approach to go after that. Okay? The second thing is durability. So and we address durability through many different ways, but the key ones are running our components as cool as we can, having the best materials we can, and understanding our parts and knowing how long they're going to last. So up on the third floor of the screen is an HPT blade, and just to give you some perspective on what it takes to make our parts durable, when that blade is operating in our engine, it's carrying a load of about 20,000 pounds. It's the equivalent of hanging a tractor-trailer truck off the end of the blade. That's the centrifugal load on that blade. And our discs will have 60 of those blades on them, so the discs are carrying 60x that, which is challenging. What makes it more challenging is that the environment that blade operates in, the temperature of the air in that environment is many hundreds of degrees hotter than the melting point of the metal the blade is manufactured from. Okay, so this is like taking a piece of taffy out on a hot summer day and just pulling on it and trying to exercise it in a way that it wouldn't creep, wouldn't stretch. Why does that matter to us in supersonic? Well, if any of you flew here today, like I did and like Joe did, the blade in that engine experienced that condition while you were in takeoff and while you were climbing up to altitude. And that's severe enough for us. We've had enough at that point. But for supersonic flight, at a super cruise condition, it is the entire flight. So as fast as you can get across the pond, 2 hours is great. That's still a lot longer than what we're doing today. And so we are investing in the cooling technology and the material technology to allow that to happen. And same with, on the lower image here is our ceramic matrix composite shroud, and then of course, advanced manufacturing like additive to enable these cooling and materials plays. And then understanding our parts and knowing when they're going to fail. And the third thing is noise. So also on that flight today that I was on, I was wearing noise-canceling headphones the entire time. And Joe's not going to make it easy on any engine manufacturer. He's going to ask us to throw an engine on the side of the airplane and maybe on the tail that allows him to fly supersonically over the ocean. And at the same time, he's going to tell us that the passenger in seat 9A doesn't want to hear anything louder than a vacuum cleaner, right? And that is something that has changed dramatically since 50 years ago. And it's through technology. And so Peter talked about moving a boom to a thump. I'm talking more about the standard noise on an engine, fan noise and exhaust noise, and how we're addressing that with new mixer technology. And the key thing is the installation of the engine on the aircraft and being able to have variable geometry around that, being able to adjust geometry to different conditions. If you've ever sat with a compressed air hose and sprayed it at a wall and changed the angle, you know that you can make it louder or quieter based on the geometry that you're spraying it at. That's essentially what we're trying to do here by having the variable geometry capability. So there's a lot of new technology available to make this possible. It continues to be investment in it. And I'm proud to say that at GE we're committed to being on the front of that, the front range of that, and continuing to invest in these technologies. Now, all that now a commercial. It's not a video commercial like Booms, but also this year we at GE Aviation are selling 100 years. It's our anniversary, and we've been celebrating it all year long. And if you are aviation enthusiasts, which I'm guessing you are, there is a blog out on the internet. You can just Google GE 100-year blog, and we've been publishing articles all year long about what we've been doing in GE for the past 100 years, including one article about the GE-4, which was the engine for that Boeing Lockheed competitor supersonic aircraft that was based in the U.S. So thank you very much for your time. I appreciate it.
Am I on? All right, well, that's it for that section, but we'll just have hopefully a couple of questions, and then after a brief discussion, we'll just open up the conversation and to questions from the audience. Not quite yet. Not quite yet. Just a quick discussion among us, and then if you have any great ideas, that would be, please share them with us. The very first thing is just a very general question. I mean, the Concorde stopped flying in 2003, and in 2003 it was retired to the museums, and ours included. And everyone assumed that was it. It was a wonderful experiment. It's come and gone, and we'll just continue on our way subsonically. 16 years later, though, things seem to be different. What's changed? And it's open to anybody.
Well, from a demand perspective, nothing's changed.
Mm-hmm.
I mean, ever since Concorde flew, you know, the need for speed is there. The idea that you could get to where you're going faster. You could get to the point where you could maybe do a day's business and return home that evening. You can connect to people worldwide and without spending days doing it. I mean, that idea is still there, and we see that, you know, the market demand for fast travel has just been constant ever since.
Yeah, I'll second that. One of the beliefs we have at Boom is that there's still a strong need for direct human connection in the world. So, you know, video conferencing and FaceTiming on your phone and those type technologies keep getting better, but there's no substitute for actually being somewhere, connecting one-on-one with people, whether that's family or coworkers or government leaders, you know, whatever. And I think there will always be a need for that. And I talked early about the impediments to travel, the time hassle and the money, and to Peter's point, the need for that is still there. And so what these type speeds can do for people who don't understand the actual reality of that time saving. You know, some people say like, oh, it's only a couple hours, how much difference does that make? We like to say it doesn't just save hours, it saves days. So as an example, right now if you want to fly from DC to London or to Paris, it's roughly a 7-hour flight. With our airplane, you can do that in about 3 hours, a little over 3 hours. So that's a 4-hour difference, but the difference is you can leave the east coast of the US early in the morning. You can get to London, for instance, by early afternoon, spend the afternoon in London at a business meeting, probably go out for drinks or even an early dinner, get back on an airplane and fly home, and with the time change, you can actually be in bed, in your own bed that evening. So you can literally, quite practically with our airplane, make a day trip to London. And so to Peter's point, that demand hasn't changed, but then to double down on what Joel's saying is 1% a year is a pretty big number when you multiply that by 50 years, right? So that's really what's enabling it today. So the demand hasn't changed, but what has changed is the technology has finally caught up, we believe, to make this feasible to where ticket prices can come down, and more importantly, perhaps, we can do this in a socially and environmentally sustainable way for the Earth.
Well, we had a discussion at dinner about the market. Now, when the Concorde was originally drawn up in the late 50s and early 60s, it was understood that it was going to seat 100 passengers, and it was not going to be the airplane for the average man. They knew, because of its expense, even in the early 60s, that it would only be first class, and as I said, first class plus. And they were hoping it would be a success, and it would lead to a second generation of SST. which seat like 250 passengers. That would have been the equivalent of the one that Boeing and Lockheed were working on here. It never happened. The thought being, greater capacity, lower seat mile costs, et cetera, et cetera. But they always understood the market was not for, the common man. It was to be high that. Has that market changed at all? I mean, it's been 50 plus years.
It has significantly. So to your point, at the time Concorde was introduced, first class certainly existed. Business class, the way we know it today, did not exist in that time frame. So at that time, first class, when you see the type of stuff Lawrence was presenting earlier, those typically were the first class cabins, not the economy class in the back. And what's happened in the meantime is the airline industry has figured out there's a middle ground that's pretty happy of give the passenger, business travelers specifically, who need to go on a short trip, can't manage the time to recover from jet lag for a couple days before they can go into their meetings. So give the passenger a larger seat, a lay flat type bed. Less perks than what the old first class used to have, where they had images of bars and very fancy meals and so forth. But that's really what the industry has gone in the meantime. So we believe, not just believe, but there's data that shows if you take today's travel and project it forward until we come into service at today's growth rates, the market we're addressing is 65 million passengers per year around the globe. And that is only business class or premium cabin passengers on overseas trips. So it's a massively different market than what Concorde was going after. And if we can get the price point down to what those travelers are paying today, which we believe we can, that is our addressable market.
Speaking of which, about how much do you think the ticket's going to cost?
So business class tickets today are vary tremendously depending on a lot of different factors, but a ticket from here to Europe, one way is on the order of $2,000 to $3,000.
Well, I work for the government, and I can't afford it, but that's, but that's not unreasonable, I know, but there's a good market, I'm sure, for that. Talking about engines, you were talking about the efficiency, but what new technologies are there to make, for the airlines, it's really, really important to pinch every last penny. And, I know the new innovations in the engines, but 1% improvement is great, but, what in the technology are there to maybe make this even more efficient?
Yeah.
Do you ever envision supersonic travel being as cost effective as subsonic?
Well, from the engine perspective, yeah, I think that's very attainable. And, they're the technologies that are going to make the operators feel the value of the technology, is for sure around performance and what materials we bring to bear to reduce fuel burn. In the end, carbon emissions is just based on how much fuel you burn, right? And the cost of operating the aircraft is based on how much fuel you burn. And so a lot of the technologies around cooling improvement and material improvement are there to address that. But also, a major factor for the airlines is utilization. A major factor for you as passengers is utilization. So what do I mean by that? You want your airplane to be at the gate when you get there, and you want to be able to fly, and you don't want it to be, you don't want maintenance to be out there while you're sitting in the cabin on a hot tarmac, right? And so the airplane being where it needs to be and ready to fly on time, a lot of that ties to how well we understand the maintenance and the parts in the engine and make sure that they are lasting as long as they need to, and that we know ahead of time before they fail. So there's a lot of technology being developed into that space to make sure utilization is on point.
I wanted to thank Joe for his comments earlier about the variable cycle engine, because in addition to the boom problem, which we've identified as the one that we'd really like to solve first, NASA has been investing in propulsion and airframe technology research, essentially to identify where those efficiencies would come from. So from the propulsion side, that variable cycle engine technology, where the engine essentially acts like a supersonic engine at supersonic speeds, but then it changes its flow streams a little bit, so it acts more like a subsonic engine when in the takeoff and landing regime. So it improves efficiency, reduces noise. So, and there's a host of structures technologies, control technologies, aerodynamic efficiency technologies that are all out there, and they may not be on the boom airliner, but they're the things that enable a succession of airliners of increasing capability that really do start to open up to beyond business class to, maybe high end, maybe it costs a little bit more, but essentially really start to make that travel available to more people.
Mm-hmm. There'll be a price point somewhere where it'll be worth it for someone to pay a little extra for that, to save 4 hours across the Atlantic. The question is, where is it?
Mm-hmm. Yeah,
and unfortunately, in capitalism, the market will tell you.
And that's what both these gentlemen are talking about, is very much a part of Boom's long-term vision of, we want to make this concept viable not just for business class travelers, but someday we see a vision where if you go fly from the East Coast to Europe, you will fly that flight supersonically, whether you're a business class passenger or economy class passenger. And I think it really doubles down on what both of them are talking about. If you look at this, the last 50 years of engine development, it has all been very guided by optimizing for a subsonic airplane. And like I started with, we're planning to use the technologies that exist today that were optimized for subsonic travel. Now, if we can make this mainstream and actually show that there's a real market here, the industry then will start to optimize in this new direction for supersonic travel. And we think in another generation or two of aircraft, we can get it to where ticket prices are incredibly affordable. That'll also then allow the airplane to be bigger, and the economies of scale make it a larger airplane much more economical as well. So you bring those two together in variable cycle, something we're very excited to see come out in the next 10 to 20 years, probably, something like that. It could be a huge game changer. Right now, there's not enough investment or not enough momentum to make that happen immediately, but we believe the numbers close for a business class airliner today, which is what we're designing in Overture, and then capitalize on that for the next version.
Great. Good luck. Given the name of your company, Boom, and Peter mentioned that it doesn't appear that you are incorporating any of NASA's technology. How loud will this aircraft be? Or are you taking steps that, to reduce that?
Yeah, so first I want to say we are huge fans of what NASA and Peter is doing on the X-59. We're very much on board with the low boom concept. Our first airplane is not going to go down that path, and the primary reason for that is we firmly believe the technology is there to make a supersonic aircraft that has a sonic boom signature that would be acceptable for overland flight. In fact, if it was just a technology problem, Peter, you might have a different opinion of this, but it potentially could be in place soon enough for the time frame of development we're talking about. I think what most people in the industry believe, though, is that the certification unknowns, especially given that it's a worldwide standard that has to be set by a lot of different countries around the world, and everybody has a different idea of how quiet is quiet enough. We did not want to place a bet on what level that needed to be on the first product we bring to market. So that's part of the answer. The second part is that just like Concorde flew mostly over oceans, we've got a tremendous market to go capture with our first entrant to market, Overture, that doesn't rely on the low boom signature type aircraft. The second part of aircraft noise, though, which both alluded to some, that some people somewhat get confused, is there's a big difference between sonic boom, which happens once the airplane is up at cruise altitude and flying supersonically, and what's called community noise, or takeoff and landing noise. That is a standard that we are very much have to meet today, because we have to go into airports, international airports all around the world, and we have to seamlessly fit in with the current airliners that are out there today. So our first aircraft will meet noise standards that will be equivalent to the subsonic airplanes that are going to be in service at that time. And as Joel pointed to, that's not a trivial problem either, especially for a supersonic airplane. That said, that is, to us, is a given that we have to go do.
I would imagine most of that noise is generated by the engines.
A lot of it.
I mean, I'd like to argue with you, but we have our share. Everybody else has their share.
Landing gear and flaps and other things make noise too.
But all airliners have that as well. It's just,
sure.
There's V-jet exhaust noise and fan noise, and especially as you're going to go to smaller, higher speed fans, that will be part of what you have to deal with on the engine. So,
yeah. But if you don't need an afterburner, that saves a lot of fuel.
Removal helps a lot. Yeah.
Well, how many think you're going to sell?
So we talked about the number of passengers, 65 million passengers worldwide, business class or premium cabin, depending on how you call it, on routes that work for us, meaning mostly over ocean routes. That transfers, if you look at that, and so that's people, passengers. If you look at it in city pairs, it's roughly 500 city pairs around the world. So 500 different routes that the airplane could fly, and then we think that then boils down to somewhere between 1,000 and 2,000 aircraft. So a significantly larger number than Concorde, which put 7 aircraft to both Air France and British Airways in service. So 14 aircraft total.
You know, which is, well, they built 20.
Yeah, they built
plus
a few
bunch of
more.
them, but they,
Yeah.
But,
Yep.
They didn't. They sold 7. The others were given away for £1.
Right.
Yeah. Well, obviously regulation is going to be a problem. I wouldn't say a problem, but it's a challenge. What's NASA learned, and for matter anyone else has learned about dealing with the regulatory authorities and how to get the permit to fly supersonically over land, and especially over populated areas? I mean, I know with the Concorde, especially when it came into New York, it was very political about the noise, and the noise was a problem here. And I don't even think people have really tackled the problem of the sonic boom, because we've never had supersonic travel over the United States, in an airliner, obviously military, but in restricted areas. So is sonic boom really a problem, or is it in people's imagination?
Well, you know, if I've talked about sonic boom to a lot of audiences, and I always describe there's essentially 2 camps. You know, the guy who lived by the military base in the 60s, oh, those sonic booms, they were great. And
Yeah.
then the people who said, you know, just can't stand it. And, you know, if you look back at when, in the 60s, when the Concorde and the USSST and the FAA really decided to do a community test, and that's really the thing that gets interesting, is when you really go out in the community and expose them to the sounds on a day-to-day basis. And they did it in Oklahoma City for a month, and you know, the results were overwhelmingly negative to the sound. So. I don't even like to use the term sonic boom. You know, I try to use thump. We try to come up with a new word, because as soon as you say boom, there's an immediate kind of negative connotation. This is not your father or your mother's sonic boom. If you imagine, you're standing outside, you're in a thunderstorm, and you get one of those ones where you see the lightning and the thunder hits immediately. Well, that's a sonic boom. And you know, 20 minutes later, the sun is out, there's a few clouds off on the horizon, and you hear that kind of distant rumble. That's what we're aiming for in terms of sound from quiet supersonic flight. So, you know, we know it's a very significant challenge. NASA has been working with the FAA and the International Civil Aviation Organization and their environmental body, you know, essentially to really put the 3 pieces together. You know, what are you going to measure? How are you going to measure it? And then finally, what are the limits? And the data from X59 is what's going to provide essentially what we call a dose response curve. You know, at this level, X number of people were annoyed, and at that level, Y number of people were annoyed. And you know, the regulators set the standard. You know, they determine how many people are going to be annoyed, because generally there will always be someone who's annoyed. But we want to put the data out there that enables a rational, technical-based decision to be made on what that level should be.
Well, thank you, gentlemen. I think we can open the floor to questions. I believe we are setting up microphones at the end of the aisle. Is that right? If you have a question, please just go see Gene or someone on the other side. That way I don't have to repeat the question and get it wrong. My hearing's not what it used to be.
Yeah.
It's got nothing to do with sonic boom.
Right.
Hello. Hi, my name is David Klein. My question is for both Boom and NASA. Both the B-1B and the TU-160 have been operating for the last 40 years, and they still operate successfully, both in low-speed takeoffs and landings that are pretty reasonable to the population, and for operating at continuous speeds at SST. So why not go with a swing wing design instead of going with deltas? We know the swing wing works. It's successful. They have hundreds of these planes out there, and they can work. So why continue with this design instead of swing wing? Thank you.
It's a great question. Aerodynamicists love swing wings. Structures engineers hate swing wings is the summary of that answer. And you're absolutely correct that there have been a bunch of successful airplanes that use that technology, the B-1, several Russian airplanes as you proposed, the F-14, F-111, and so forth. In general, and you know, a bunch of aircraft have looked at this, or companies, including Boeing and Lockheed back in the days of the American SST programs. At Boom, we've looked at it very briefly. In general, the weight penalty for that, the weight penalty for the structural considerations for a swing wing typically do not outweigh, or they do outweigh the aerodynamic benefit you get from that. So you can make an airplane that is successful. However, something like a B-1 or most military aircraft are not optimized in the same way for fuel economy the way an airline has to be. And unfortunately, the trade just doesn't typically work out, especially when you consider not just the structural implications, but the fact that in a supersonic airplane, you probably need to put fuel in the wings. So then you've got to do fuel transfer through that joint and so forth. So, Peter, I'd love your take on that if you had any other views.
No, I agree entirely with everything that you said. Additionally, you know, the the B-1 and the TU-160, you know, if you heard their sonic boom, you would know what unacceptable is. If you look at, you know, if you look at the design of this airplane, to achieve a quiet supersonic design, you really need to start out. That's your #1 design driver. Everything about the shape of that airplane is all about first achieving low sonic boom, a low quiet supersonic flight, and then achieving efficiency, including the wing design. And a swing wing design, it creates an integration challenge. You've got that hinge and all the associated structure that holds that hinge in place, makes it very challenging to integrate the wing and the fuselage in a way that mitigates the shock wave formation and allows you to have a quiet supersonic signature.
Hi, thank you all for your comments tonight. Something that I've seen with a lot of futuristic technologies, whether it's supersonic flight or the Hyperloop or whatnot, is that it's just a lot easier to create a visual rendering and videos and the like than to actually bring something to market and overcome all the challenges there. So my question to those of you on the industry side is, what would you say to skeptics to persuade us that this is something that will be coming to market in a relatively short time frame? And to the rest of the panel, I'm curious, what are some of the obstacles that might prevent this technology from coming about as soon as we might expect or want?
Yeah, so from Broom's perspective, I think to answer that question is you can just look at the track record we've had to date. So if you look at our investment in the company, like I said earlier, we've raised $150 million to date from investors, which funds the supersonic demonstrator that we're building. We've got pre-orders for 30 aircraft from 2 airlines, so Japan Airlines and Virgin Group. And one of those, Japan Airlines, has actually invested in the company as well. So I think seeing commitment like that at this stage, before we even have a firm design, is a really a huge vote of confidence that the airlines really want this, and they see that what we are bringing to market could be a huge differentiator and help them grow their business, and they're giving us their support. And I think the third reason that you could point to where this is viable is kind of also what I said around the fact that we're not really inventing anything new. There's no like magical material or way of flying that has to be invented for this to happen. We can literally take today's technologies and certify them, and that's a very important point. I love what Joel was saying earlier about safety being priority 1. We like to say at Boom as job number 1, essentially the same thing. And really what that comes down to is certification with the FAA or with EASA or the international regulatory bodies. So that's sort of a double-edged sword. On one hand, there's a lot of regulations you got to meet. On the other hand, the rules are sitting there right in front of us. We know exactly what we have to go do to make this airplane viable and to meet the safety bar that the world is going to demand. And to Joel's point, like there can be no accidents, there can be no failures in that system. But we know what those rules are. We have a team in place who's been through that before, and that's one of the big reasons we're building our demonstrator, is as a company to start building that into our culture and to really take the safety aspect and the reliability aspect both from day one. So I think when you look at those pieces, one at a time, like all of that tells a plausible story that there's really nothing that is standing in our way other than the fact that we are a startup. This is a new company, a new project, and it's a complex project to go undertake. But that's within our power to go do, and we're getting a lot of support, whether it's from investors or customers or regulators, that really, all three of those really want to see this happen and are partnering with us to do that.
Hi, my name's Lily. Thank you all very much for your time tonight. My question is basically, so I'm assuming that supersonic planes require more advanced training for pilots to fly. And so if that's true, what will that training look like? And will there be a problem finding enough qualified pilots if supersonic flights become more widespread?
So in general, if you look even starting back to Concorde, the qualifications to fly Concorde were really no different than any other airliner of the time. Now, the highest time and highest seniority pilots tended to fly that, but more because it was a prestige thing than it was necessarily a skill set thing. So if you look at the airline industry today, every transport category aircraft, so anything that Boeing or Airbus produces, requires what's called a type rating, which is a special set of training you go through to be able to specifically fly that model of airplane. And really what that process is teaching you is the unique systems on that airplane and how to be able to deal with system failures and safely land the airplane in case of emergencies. So our airplane will be no different in that. Our airplane will require a type rating to fly, just like a 737 or 787. But that said, the actual piloting skill, due to automation of systems and so forth, should really be not a lot different than what it takes to fly a current. If you're an airline transport pilot today, you should be able to transfer into our airplane in a relatively straightforward manner.
Hi, my name is Muhtasim. I first wanted to say thank you for coming out here and giving us the opportunity to be here and learning. My question to you all is, what advice would you give to youth who are looking to pursue careers in space and aviation?
I'd love to jump in on that one right out of the gate. I was going to say on my first chart that things are so exciting right now in the aviation industry that if you are an engineer working in a different industry, you should go back and visit your guidance counselor from high school and ask them why you are in a different industry. There is a lot of going on. The industry is growing. It's very, very much driven by technology. So, and it's across all different disciplines within the industry, even to maintenance. Even finding enough people that can be qualified to maintain the products is becoming a challenge. So there's a lot of opportunity in the industry. But even beyond the fact that there's opportunity, there's a lot of awesome stuff to go work on, from UAVs to autonomy to supersonic and the next generation of products for fuel efficiency with electrification, et cetera. Just that whole, what an airplane looks like and how it integrates with all of its subsystems is going to change in the next 20 years. And so if you're a youth who's thinking about entering the industry, this is an opportunity for you to get in on the front end of that and make a difference in what the products look like in the future. And it's all in a constrained environment, because our society wants us to be better around how we handle emissions and impact the planet, and better around noise and other things. And so we're engineers, we like to solve tough problems. That's the definition of a tough problem, is to go do all of that in that constrained environment. So for me, I wouldn't trade it for any other opportunity. Would either of you?
No, I just pile on with what Joel said. It really is an exciting time to be in aerospace, and there's so many disciplines with engineering and mechanical and so many different backgrounds that there are opportunities growing. So depending on where you are in your education career, if you're early on, you obviously want to focus on the STEM courses. Don't forget English, though, because we really do need to, or language, because we really do need to be able to communicate.
As you're all learning tonight.
What we learn. Yes, that's right. Bad or good. And but you don't have to. The good thing is you don't have to. Aeronautical engineering is kind of the traditional discipline, but there's so much more beyond that. Anything that you find an interest in, you can really pursue at the undergraduate level, and there are opportunities that start from there.
Hi, my name is Bob. Could you tell us a little bit more about the thump that is the new objective?
Sure. I'll try to give the elevator version. Any airplane, anything flying faster than sound, any pressure, any change in the flow creates a shock wave. It's essentially the air doesn't know the plane is coming because it's going faster than the pressure change can be communicated through the air. So it changes instantaneously. Now up near the airplane, you've got all kinds of shock waves forming off of every component. You got one off the nose, off the canopy, off the wing, the engine inlets, et cetera, et cetera, et cetera. They're all different strengths, and they're all kind of randomly spaced along the airplane. Each of those shock waves causes a small change in temperature, which causes a small change in the speed of sound, which means each wave is going a little bit at different speed. So on a typical supersonic airplane, within a few body lengths of the airplane, all those shocks have essentially merged into the two. And that becomes a very stable acoustic system that travels all the way to the ground, and you hear, even though it's attenuated a great deal by the time it reaches you, it's still a very impulsive sound, and even though it's actually a very small change in pressure, your ear hears it because of the impulsive, rapid change in it. So the idea is to prevent those shock waves from getting together. So on the X-59, the entire airplane is shaped so that, in general, the shock waves are of similar strength, and they're distributed evenly along the airplane. So they don't tend to pile up on each other, and the atmosphere works on each wave individually, so you get maximum attenuation from each wave, and at the end you get something that, if you plot it, it looks more like a sine wave than an N with the two sharp peaks like a typical sonic boom.
That was a pretty good explanation there.
And someday maybe we'll rename boom into thump.
Maybe so.
My name is Flint Webb. I was an old engine guy. I used to work for both Pratt & Whitney and GE. And so I'm curious about your variable cycles. Are you looking at changing the inlet area like they do on the SR-71? Or are you looking at just looking at changing the attack angle on compressor blades and that kind of stuff? Combination.
Sorry, were you going to go?
I'll follow up after.
Okay, so I'll talk about the inlet because that's the part of the airplane that we own. And so there's different ways of doing it. You know, the Concorde used what's called a 2D variable inlet, where the inlet is somewhat squarish and has inlet ramps that change to different angles depending on flight speed. That is what you show, or we showed in our rendering here. There's another version called an axisymmetric inlet, which is similar to what Blackbird had. That can also be variable, which Blackbird actually was. That spike in the front, or that cone, can move in and out of the rest of the inlet and change the area and the geometry. We're looking at both options still at the moment. There's pros and cons to each. Once you get up to a certain speed, in the Mach 2 2.2 range, you almost need the variable geometry to make the airflow work properly between high speed and low speed. I don't want to speak directly to the NASA design, but there's a slightly lower Mach number. I believe you have fixed geometry, if that's right, yes. Which works quite well at a slightly slower Mach number. So at the speeds we're flying, though, at Mach 2.2, we will likely have, almost certainly have variable geometry in one of those ways I just talked about. That is different than what's referred to as a variable cycle engine, which is variable bits inside the engine, which Joel can probably
So I'll answer that.
To.
So that's correct. There's two pieces of terminology here. One is the variable installation geometry, which is that translating inlet or other type of variable inlet, which is a major part of how we make this successful for going to Mach 2.2. The second piece of terminology is variable cycle, which is variable geometry within the engine that allows you to change the bypass ratio of the engine, essentially. So it allows you to get to a high bypass operation when you want it, or a low bypass operation when you need the capability. So that's internal to the engine, but the more important thing, I think, relative to the supersonic application is the variable inlet.
So unfortunately, this is our last question, but I think a few will be staying after the lecture, so there might be more.
Hi, my name is Afnan. She said this was the last question. Actually, I had two, but I'll go with one of them. It was in regards to, I know we talked about that the last commercial supersonic airliner was flown in 2003, which was the Concorde. And the main issue why we stopped was because of all the noise that it was causing. I guess it's more hypothetical. Would it have been more efficient to, say, keep Concordes or market in a way we would have more Concordes on like coastal airports? So we're talking about transatlantic. So if we're going to over the ocean, there's nobody living in the middle of the ocean. Would that have worked?
Yeah, I think takeoff noise was certainly an impact on Concorde. However, at the time, Concorde was within the legal limits of what an airplane could take off and land as far as community noise goes. Those standards have gotten more stringent since then, but I don't think that in itself was really why Concorde went away. It certainly didn't help the case, but it wasn't that specifically. It was more the economics of it, which came back to fuel burn and the number of airplanes and the unit economics with only having a few. So I personally wish Concordes were still flying because maybe I would have gotten a chance to fly on one. But that said, that's given us even more impetus as Boom to go and do what we're doing now, because it's frustrating that technology used to exist and we cannot do that today.
All right, thank you very much. Thank you all for coming. Well, I'll just it doesn't matter. Thank you all for coming. This was a most entertaining and engaging conversation. I sure hope Boom can pull it off, because it really is the way to go. It's remarkable technology, and I'm so glad to see so many people working seriously on it. And maybe in a couple of years, well, more than a couple of years, but soon we'll be able to fly supersonically anywhere around the world. That'd be great. A little bookkeeping. Lawrence will be outside at our welcome desk, our Southwest Airlines welcome desk, to meet and greet and sign books if you'd like to meet him. And just for a practical standpoint, when you exit, please exit through the exit at the top of the steps. Just walking down the steps is not safe. Thank you very much for coming.